So I want to talk to you a little bit about this cool project we've got going on called Mavis. Now, Mavis, some of you, if you were at the last one, you heard me talking a little bit about this, and we thought we'd be a little further along at this point, but the funding took way longer than it should have. But this is actually a thing that is happening now. I'm going to show you a little bit of the development that's going on with it in this presentation, tell you what it is, and and also talk a little bit about some other things related to AI and machine learning and sort of how they work, what we think these things do. Mavis, if you're not familiar, this is Machine Assisted Vulnerability Identification System. I've got Bender in there. I don't know. I'm thinking about doing something to Bender to make him more of a Mavis icon there. But before we jump into Mavis and how it actually works, I want to talk about what it is neural networks are really learning and what it is that really drives large language models. Because it continues to be true. I mean, it's amazing when you think about how many years have gone by since OpenAI released ChatGPT. It's been years already. Can you believe it? And it is still driving headlines. LLMs have really captured people's imagination when it comes to artificial intelligence. So one of the things that's so fascinating about this is that while ChatGPT is amazing, and no doubt you know of other ones like Llama and Bard and others at this point, but as amazing as it is, and as amazing as it was for its time, we already had better large language models before ChatGPT, years before. What OpenAI really did well was turn that into a thing pushed on the internet with marketing that people could now talk to it and see that artificial intelligence is a thing. So it's a really amazing tool, but we do also see that many organizations have a directive going on saying that they need to use artificial intelligence, find ways to use AI, or even paying for AI products and AI registrations and services. But quite frequently, management has not managed to articulate exactly what it is they expect us to do with artificial intelligence. That's a great thing from a marketing point of view, because if we can just put AI on a product, people are going to want to buy it because they have this money to spend. But there's also a little bit of a downside, because as much as LLMs have captured people's attention and it's what people think of when they think of AI today, finding really good security applications for large language models can be a little bit challenging. Mavis is sort of an example of that, though it's not really a large language model. Shh, don't tell anybody. There are some other amazing things, though, that we can do with those. But how are they really working? What are these neural networks really doing? So I like doing demonstrations of things. So if I can figure out where my terminals are here, let me just get this guy up here. And I will make this a little bit bigger. This I'm not talking through this whole thing here. This is actually an example of using AI to do log anomaly detection. I know there's a talk coming up that's going to be amazing, automating log analysis. I have no idea the approach that's going to be used there, but this is just an example of how this can be done. And I'm doing it using a particular technique called an autoencoder. Now, I actually feel like maybe I should just show you what an autoencoder looks like. Hold on, I've lost my, where's my media center? It disappeared on me. There it is. And let me just get that up and put that over here. Okay. So this is an example of what an autoencoder does, or at least the structure of what one looks like. An autoencoder, it's a kind of neural network. We could say, in a sense, it's a sort of auto-regressive. There's a lot of words we can attach to this. And the goal in an autoencoder is quite different than most neural networks. The goal in an autoencoder is to put data in on the left-hand side, the input, and we're going to try to create an output that's exactly the same size out of the right-hand side. Now, in the middle, you can see it's got sort of this hourglass shape to it. And while that is not a requirement, usually we draw these as being symmetrical hourglass things, the really critical piece is that it has that choke. That choke is limiting how much information can pass through the neural network. That's really what it does. So if I let this play a little bit and we train the network by maybe putting in pictures of chairs on the left-hand side, we then are asking the network to figure out how to take that input, boil it down into that choke layer, and then reinflate it, decode that back into a chair. What's the purpose of this? It doesn't feel particularly useful. It actually is incredibly useful. Not only are autoencoders at the very root of how generative AI solutions work. Now, don't mistake me. I'm not saying that when you use a generative model like an LLM, it's an autoencoder. I'm not saying that at all. But this is the ancestor of everything we're using for generative AI. This whole idea about how we do this training. In this particular case, it's taking that image in on the left, and it's then trying to learn how it can take that down into that choke layer and then reinflate it to recreate a chair. And I'm sure looking at this, you can see that the output is a chair, but it's definitely not the same chair. That's okay. Is it chair-like? Does it have all of the qualities, all of the features that you would expect a chair to have? It has legs, there's a seat, it's even got arms. The one on the left doesn't have arms, but that's okay. Chairs have arms. It's got a chair back. But we don't just train this using one chair. We're going to train it using thousands, hundreds of thousands, maybe millions of chairs. So here we have another chair coming in, and out of the right-hand side, we again have something chair-like coming out. What the autoencoder allows us to do is to build a network that is effectively a single class classifier. Building classifiers in neural networks or in machine learning in general, because we can build and have built classifiers for many years before neural networks were ever used for this. So a classifier is just something that can decide what something is using some method. In machine learning, that method is pretty much just going to be math. So this is working out some math thing to be able to do some classification. But wait, now, classification, how is this classifying anything? All I'm doing is getting a chair out. Well, I said that it's a single class classifier, and it's particularly useful for solving a very specific problem in machine learning and in security. We are very, very often interested in knowing about unusual stuff. You may have heard me and John speaking before the event began, and we were talking about how in threat hunting, one strategy toward it is just saying, I know what things should look like. I'm looking for things that look weird. Show me the weird stuff. Let me find weird. That's a way that we can do anomaly detection. Now, when someone begins learning about machine learning and trying to build things that will detect anomalies, one of the big problems they first run into is, how do I tell it what's weird? How many different ways can things be weird? There's millions of ways. There's maybe an infinity of ways. So is it possible, instead of trying to define what is weird, to define what's normal? And that even feels like things we have done for decades with log analysis, where we could, for instance, create rules, maybe regular expressions, where we're excluding normal events so that only the unusual events appear. So this is not a new idea. Why is AI useful for it, though? Where do autoencoders fit into this? Well, see, the thing is that 30 years ago, we could absolutely create just a handful of regular expressions and find unusual log entries. But today, the scale of systems we are running is vastly larger. How can we create all of those regular expressions? And I can't create the regular expressions until I already know what's normal, or vice versa, until someone tells me what's unusual. It's one of the big problems that people who run sims have. Nobody knows who the guy is who runs the sim until something's wrong. And then during the incident analysis, everybody wants to know, why didn't the sim give us an alert? And the poor person who runs the sim says, I can only give alerts for things you tell me are bad. I don't know they're bad until you tell me. Is there a way we could speed that up? Is there a way that we could maybe leverage machine learning to solve that problem? One of the ways we can do that is with autoencoders. So I said this is a single class classifier. I said one of the problems that people new to machine learning have is, how do I tell it I want to know about unusual. Tell me about the anomaly. Here's how. Because if I now give this something that is not a chair after training it to identify chairs, the thing that comes out of the other side looks nothing like a chair and absolutely nothing like the original input. How is that helpful? Well, when training neural networks, when people first get started, one of the things they tend to fixate on is the accuracy. How well is it performing? But as you become a little bit more advanced, you not only begin to look for different measures, but you begin to realize that the loss, the error, how wrong it is a much more important measure than how accurate it is. In an autoencoder, we are specifically only looking at the loss. And we use a very specific name for this. So loss, or how wrong it is, it's called reconstruction loss. Looking at this picture here, if we put Dwayne "The Rock" Johnson in on the left and a turnip comes out of the other side, the reconstruction loss on this is absolutely astronomical. But if we go back a little bit and we look at a chair, if I put a chair in on the left and get a chair out of the right, yeah, they're not the same chair, but the reconstruction loss is far lower. And we've now turned this into really a pretty simple problem. I can simply ask, what does the reconstruction loss look like? If it's above a certain threshold, we're going to say that's anomalous. And if it's below that threshold, that's probably normal. Let's take a look at this in practice. So I had this example where I'm loading in log data. Here it is right here, a bunch of log data. This is coming out of just a normal system log off a machine. And I'm going to do some pre-processing on it. I'm not going to get into detail of that pre-processing for this. We just don't have the time. This is one of the labs we do in 595, so there's a lot more detail in there. But we're going to pre-process it a bit. I'm just going to clean it up. I'm going to strip out some numbers. I'm just trying to make it so that only things that don't change much are showing up in the log entry. That's really all I'm doing, because my autoencoder is going to be sensitive to things that change. And after doing that, I'm just going to go ahead and train this network. So I've got down here a model. Again, the details of this, don't worry about it for the purposes of what we're doing. We're starting off with some large input. We're bringing that down through a funnel, and then we're bringing it back out. It's that hourglass shape. That's what this is. And after training this, so let's get to the good stuff down here. I've got some, I need to go slowly. Got some examples. Okay, accuracy, loss, whatever. Here it is. Okay. So here, all right, let me stop there. These entries here, what I'm printing out to you, these are log entries coming out of the live system. That log entry, the line I have highlighted right now, that's what appeared in the log. When we push that through the autoencoder, this is what comes out. And I'm sure you look at that and say, yeah, so, I mean, what does that mean? That doesn't seem motivating at all. Well, the point is that it's the same. And they're not all the same, by the way. Like this one here, this letter was not reconstructed correctly. So it is really, I said reconstructing, it is really generating a log entry. When we take the data and push it in on the left, it's then going to pull that down into that much smaller space, that choke that we had there. We call it a latent space, or the latent dimensions. It's the limited information that we allow to pass through from the part that encodes the entry to the part that decodes the entry. So from that latent space, it's decoding this back into that log entry. Oh, okay, so it actually is doing something pretty complicated here. And you can see further down, and again, it gets a little bit wrong. But even where it's wrong, how far away from right is it? Remember that term I used, reconstruction loss? That's all that is. How far away from right are you? How does this help? This is a single class classifier, and I have trained it to identify normal events within my logs. I have up here, I have up here somewhere, hold on. I have up here, here they are. I have some other entries that we're about to run through that network. These, these are not normal log entries. Now, how do I know they're not normal? I know they're not normal because I manually wrote these by hand. I just made them up. I know they're not real. And I hope they sound somewhat convincing. And maybe they're close to what real log messages look like, but these cannot be normal log entries for my systems because I made them up. As good as they look, can we detect that with the neural network? Let me scroll back down. So we saw the ones that we reconstructed from known log entries. Here are the reconstructions of my fake entries. So as good as that looks, SSHD failed login attempt by Margie. I don't know if that's the real, what that really looks like, but I can tell you for sure that isn't anywhere in the training data because look at how that's reconstructed. Compare again. How far away from the original are these? How far away are these? These are very clearly different, wildly different. And we can measure that. We measure it numerically. We create a numeric measure of what that loss is. I'm here just turning it back into words or into letters to make it a little bit more visual, to make it more interesting for us. I do just want to add one thing about this. In the real world, I do this, but I don't do it quite this way. The way I'm doing it here is I'm actually generating these log events from the autoencoder character by character. And I'm doing them all at one go. There are other kinds of neural networks, long short-term memories or recurrent neural networks that actually generate one thing at a time. This generates all of them simultaneously, but I'm generating them at the character level. In the real world, I don't do it that way. It's not very efficient. Instead, I greatly prefer to encode these more at the word level. And I use a thing called embeddings, which we're going to talk about in a moment. Okay, so we can do some anomaly detection with this, but what exactly is being learned in there? I want to pull this one up over here. So I've got another autoencoder here. This one's a little bit different, and it's a better example, perhaps, for what it is that's being learned. And let me just scroll down to where the training has happened. So I have fed this in a whole bunch of handwritten digits. These are the MNIST digits. It's a standardized set of handwritten digits, and usually the task is to create a classifier that can identify what the number is. But I'm using it differently here. What I've done is I have created an autoencoder of specific kind, a variational autoencoder, and I'm asking it to learn about the mean and the variance, math things, the statistics, the distribution of these characters. And what I'm looking at on the left-hand side is an original character, and the right-hand side is something coming out of the autoencoder. Well, the thing on the left is a 5. The thing on the right is, well, sort of 5-like. I don't know, you could make an argument that looks like a 3 as well, but it's got most of the things I'd need for a 5. There's a 0, there's a 4 or a 9. We've got a 1, there's another 9/4, there's a 2. But to make this more interesting, to make it a little bit more understandable, I said that what I have built here is a variational autoencoder. Normally, when we just train an autoencoder, our expectation is that it will learn in that latent space the most important characteristics of the information to be able to reconstruct it. But in a variational autoencoder, it's a little bit different. I'm specifically influencing it to learn the mean and the variance, which means that I can use these sliders now, and I can slide this around, and you can see, oh, we're generating really every kind of character that appears anywhere in that data set. These are not those specific characters, but it's the entire distribution of what's possible. So what's being learned, there's an expectation about what gets picked up there. Now, with that understanding, or with that information, let's take this a step further. Let me see where I am. So what I have here is, do I have the time to do this? I'm not sure that I really do. I'm just going to tell this to restart and run, and I'm going to show you the output of it, and then jump over to the thing that we're doing with Mavis. So what I'm doing in this particular, in this notebook, and this comes out of a new class I'll tell you about in a minute or two, is we are building word embeddings. Word embeddings. In an autoencoder, my expectation is that it learns the most important characteristics of the data. In a variational autoencoder, my expectation is that it's going to learn the variance and the standard deviation. I'm influencing that to happen. That's what's being learned in the neural network. When I train this word embeddings, oh, it looks like something failed somewhere. Hold on. Let's see why this is unhappy. Oh, that doesn't look good. Why are you unhappy? Do I want to fix this right now? I don't really want to fix this right now. I'm going to, oh, I'm out of memory. So that's not a terrible problem to have. It's because I've got multiple things going on in this system. Let me see. I think I can open up a canned version of that. Uh, I'm not even going to bother. So in learning the word embeddings, it's learning about relationships between the words. And that's a really interesting idea because it never really sees the words. We just represents the words. We represent the words as numbers to the network. What I'm doing here then is going a step beyond that. What I'm doing is training a neural network to learn about the patterns that show up in source code. And if I scroll down a bit, you can see this is actually actively training. I told you we're making a lot of progress on this right now. Just scoot down to the bottom here. Does this, that event hasn't finished training. Here is a smaller data set from yesterday. That's less interesting. Here's the part that really matters. What you're looking at in this cell right here, these are small chunks of code. It doesn't look like code. This was originally C code. And the way that Mavis works, it's a very interesting idea. We're taking a different approach than what most people are doing with large language models. Many people are trying to use large language models to solve every problem there is. There was an article a few weeks ago about some MIT researchers who managed to take a large language model and get it to find manufacturing anomalies on an assembly line. Wow, that's amazing. It took them months to do it, and most of that time was figuring out how to take the sensor data from the assembly line and turn it into words that it could give to a large language model. Do they feel wrong about this approach? They feel like we could have solved that problem far more simply just using data analysis? Yes. People are trying to use large language models like it's a big hammer, and they're trying to hit everything they can see with that hammer. I'm not sure that's the right way to go. So with Mavis, we're doing sort of a stop in the middle. I brought this slide up because it says here, custom embeddings built from parse trees. Could we use a large language model to try to do code analysis? Well, sure. But that would require an enormous amount of training. And there's the whole problem of hallucination. So instead, we're leveraging some of the technology under large language models. They're driven by word embeddings, word embedding. When we train it, our expectation. So autoencoder was core information. Variational autoencoder was mean and variance. Embedding is important meanings and relationships between the words. And then those relationships are what are being driven through the transformers inside of the decoders that the large language models are using. And they're simply generating the next most likely term, sometimes influenced by a thing we call temperature, that adds a bit of randomness effectively to which words get picked in order to generate results. But these relationships between the words are what let that happen. It's the embeddings. You can think of what Mavis is doing as stopping halfway. We're not going to a large language model. I'm not trying to generate code. We are simply learning embeddings for what the parse tree looks like. So if you take source code, rather than process that directly, we're taking an intermediate representation. One of the things the compiler does is tokenize it and then turn it into a parse tree before it's turned into machine code. So we're building embeddings based on parse trees. Here I have just took some random samples out of some parse trees, and using the embeddings we trained, a limited set, I can now measure similarity of code. And that's what these numbers are. So I can see that these first two pieces of code have a much higher number. Those are much more similar than any other combination of these code samples. So these two chunks of code here, these two chunks of code here, and then this is the parse tree. I understand it doesn't look, but even though the numbers are not the same or in the same order, those two are much more similar than, say, these two. How does that help? Because once we've extracted those out, we can now build embeddings for known vulnerable code. So using the CVE database and pulling out diffs from source trees, showing us where the vulnerable code was that was patched, we're able to push that into a vector store. How is that helpful for you? Because the way Mavis will function is you now can put a webhook into your GitLab or your GitHub or whatever your DevOps is, so that when a code change is pushed in, that will trigger the webhook that triggers Mavis. And Mavis just takes the changed code you have submitted, it vectorizes it, and then checks to see if that code is similar to any known vulnerable patterns. It doesn't mean your code is vulnerable. It does mean someone should look at that code closely so it can help to trigger real code review, which is something we tend to be very, very bad at. So that's what Mavis is about. Right now, we're in the middle of the training of the embeddings. We're doing it for C first. That's a work in progress. As you can see, it's running right now. We've already got the CVE and the diff stuff working. So probably another month, and there's going to be a product out there in GitHub that you can go grab. This whole thing is free. There is something else I just want to tell you about, though, and it's connected to this idea of embeddings and LLMs. I hate to feel salesy, but there's an opportunity right now. I do not think I have ever seen a SANS class that you can buy for this amount of money. We are running a beta trial for a class that will purely be on demand, Sec 495, which is if you need to use LLMs and you need to worry about retrieval augmented generation, this is how to build RAG stuff. And it's from the basics all the way through how to build contextual RAG, which is the cutting edge stuff Anthropic is doing, and how to build an agentic RAG solutions and to do prompt injection prevention, all that kind of stuff. It's a single day class. It's running on November 6th, and it has a very limited registration. So if that sounds like anything you need to do, and you have at least an intermediate Python background, you might want to sign up for that class. So this QR code works. Sorry, my QR code doesn't. I'll get that fixed during one of the breaks. And if you want information about that, you can reach out to me. Again, my LinkedIn information is in the Slack channel. And there's other classes we've got too that are going on, really interesting stuff. But I'm gonna stop here.